So question 16 of exercise momentum and collision. This is a structure question. The first 15 questions were the MCQs. So in this question, the photograph shows a jumping toy. The head is pushed onto the base and compressing a spring when releases the spring expand and the toy jump into the air. A student investigated the toy and the student placed a toy on the balance and measured the force required to compress is about 14 Newton. When the spring is fully compressed by 1.7 centimeters, the toy has launched its the toy was launched. It jumped to a height of 1.5 meter. You can see in the next picture. This is what actually happened when a toy is like a spring is being compressed, and when we release, the toy jumps about like 1.5 meter above. Not 1.5 meter. It is 1.5 meter above the ground. Show that the maximum energy stored in the compressed spring is about 0.1 joules. How we can work out the energy stored in the spring? So you have to recall the formula because there are formulas related to AS you will also use. The energy stored in the spring, compressed spring, that is half force into extension or force into compression. This is a formula to know the elastic energy stored. So in this case, it will be half. The force which we applied, that is 40. The height, it's not like the height it moved, it's the height, how much it is being compressed. So it is compressed 1.7 centimeters. So we have to convert into meter divided by 100. So 0.017. That will be in meter. So this will give us 0.119 joules. So that is the energy stored in the spring. The next part, initially the spring was fully compressed, as you can see here. As a toy was released, the head accelerates upward, like the head is moving upward, until the spring is uncompressed. Like this part, the spring was uncompressed. And then head pulls the base upward, like both head and the base will move upward, like the head and the base is being pulled against the gravity or move up. The student used the elastic potential energy stored in the spring to determine the maximum speed of the head. So we need the maximum speed of the head. The student used the gravitational energy gained by the whole toy to determine the initial upward speed. Determine whether the toy obeys the law of conservation of momentum using the values of the speed calculated in this way. The mass of the head is 6.4 grams. The mass of the whole toy is 7.2 grams. And the maximum height which the toy gained, that is equals to 1.5 meter. So we will use a conservation. First, we'll use a idea that when as you can see, when the toy is completely compressed and it is released, the head is moving upward. So means we can say that elastic strain energy which was stored here, the elastic strain energy which is stored here is equals to kinetic energy of the head. And then the kinetic energy of the head is actually equals to, it rises to a certain height. So it is equals to the gravitational potential energy of the head and the base. You can use this method. So first, we will use the elastic strain energy to find the speed of the head. And then we'll find the momentum of the head as well. Then we will find the total gravitational potential and energy of this whole toy. And after getting the total gravitational potential energy of the toy, we'll find the speed at which this toy was moving. The whole toy, like as you can see, this is a moment, it is the whole toy is being lifted. So the head and the base will move together with the same speed. So we will find the speed of the whole toy. And we will use the conservation of the momentum, like the momentum should be conserved. So we'll find the initial momentum. The initial momentum is only due to the head. And the final momentum is the momentum of the whole toy. So the initial, if it is following the conservation of the momentum of the head must be equal to the momentum of the toy. Because like first head was moving and then the head and the base is moving, like the whole toy move upward. So first part, we'll find the speed of the head. So how to work out the speed of the head? We'll consider that the elastic strain energy which was stored in the spring equals to kinetic energy of the head. So elastic strain energy we calculated in the previous part, 0.119. And kinetic energy of the head is half. M is a mass of the head that is given in kilogram, in gram. We have to convert into kilogram. So we have to divide by 1000. So it will be equals to, because it is 6.4 gram. So we can say 6.4 into 10 to the power minus 3 as we divide by 1000 into V square. So it will be 0.119 times 2 divided by 6.4 into 10 to the power minus 3 V square, and then take a root to get the value for V. So the speed of the head is 6.1 meter per second. That's the speed at which the head will move. And now we'll find the momentum of the head, because according to conservation of momentum, the total momentum of the head as it was moving equals to the momentum of the toy, because the momentum must be conserved. So before and after must be same. This will be the momentum before and this is the momentum after. So momentum of before, that is mass into velocity, 6.4 into 10 to the power minus 3, the mass, and the velocity 6.1. We multiply. So we'll get the momentum of the head, which is 0.039 kilogram meter per second. The second part, we need the speed of the toy. So as we know, the toy rises above the ground to a height of 1.5 meters. So second part, we need the speed of the toy. Here, because it rises to a certain height, so we can say the GPE, the gravitational potential energy, is equals to kinetic energy. Like the kinetic energy at this point for the toy is equals to GPE when it rises to a certain height. So gravitational potential energy is mgh. So mgh is equals to half mv square. So m is the mass of the whole toy, which is 7.2 kilogram into gravity 9.8 into a height 1.5 equals to half the mass of the whole toy, which is 7.2 into 10 to the power minus 3, and then v square. I can also do like this. I can cancel m with m, so I can say gh is equals to half v square, and I'll get the speed of the toy at this point. And We just simplify, like mass cancel with mass. So it will be 2 into 9.8 into 1.5 in a root. That's equal to V. The speed of the whole toy, that is equals to 5.24 meter per second. And then momentum after. So momentum after is equals to mass multiplied by velocity. So mass of the whole toy is 0.0072 or 7.2 exponent minus 3 times the speed 5.24. So this will be 0.039 kilogram meter per second. So momentum before was this. This is the momentum after and before are same. So what we can say, the momentum is conserved. Is it clear discussion? So in the next question, which is also related to momentum, the photograph shows an airplane which is powered by two engines. When the airplane is cruising, air enters the engine at a speed of 252 meter per second and ejected at a higher speed, providing a thrust to the airplane. The mass of the air ejected by one of the engine in 1 minute is 34,600 kilograms. Show that the total thrust provided by the engines. So it's we will calculate the thrust of one engine and then simply will multiply by 2. Or you can solve the other way. Calculate the relative speed at which the air is ejected by the airplane. So we need the final speed here. We have the formula that impulse is equals to change in momentum, or the force multiplied by time is equals to impulse, which is final momentum minus initial moment. We need because a total thrust provided by the engine is 138 kilonewton. So we can write here 138 kilonewton, 138 into 10 power 3. And that is for both engines. Look, some values are given for one, some are given for the two. As like the mass is given for one, so and time is in 1 minute, time must be in seconds, so this will be 60. The total mass, because if I take m common, that is also fine. This is the mass of the air which is ejected by one of the engine, but total will be twice. So it will be, the mass will be 34,600 times 2. Final velocity minus the mass is 34,600 times 2. The initial velocity, which is 252. (34,600) times 2 is a common factor here. So it will be V minus 252. And 138 into 10 power 3 times 60. This whole is multiplied, other side will be divided. So it will be 138 into 10 power 3 times 60 divided by 34,600 times 2. That is V minus 252. And this whole factor minus 252, this whole factor is 120. So we can say 120 is equals to V minus 252. Minus 252, it will be added there. 120 plus 252. So that is equals to 372. So the speed at which it is ejected, that is 372 meter per second. So this was question 17.